everybody. So this is lecture number 6 from modern control theory. In this lecture we will be considering about the Zordon canonical form representation of the systems. So here it is also a canonical form like diagonal canonical form. Basically canonical forms are the forms of the systems representation which are having minimum number of elements, and these are of two types: diagonal canonical form and Zordon canonical form. If your eigenvalues are distinct and real, then these can be realized by the diagonal canonical form. But if your eigenvalues are repeated, real but repeated, in that case a new form, that is the Zordon canonical form, would be considered. In last lecture we have discussed about the diagonal canonical form, that is lecture number 5. Now it is also based on the partial fraction of the transfer function and useful for evaluating the countability, the observability, the state transition matrix, and the model order reduction techniques. It is not covered in this model order reduction is the part of the MTech, so here it is of no use to discuss about, and other forms would be, or other applications would be considered in coming sessions. So this is Zordon canonical form. We know that all of the elements of the eigenvalues, that is the roots of the system, would be located on the diagonal, and strictly for the repeated roots, and sometimes it is the combination of repeated roots and the distinct roots. So this is the form of representation of the system where we can have the repeated roots with distinct roots as well. So here one example we are considering for the system which is having repeated roots only, and another example we would be considering about the system which is having repeated as well as distinct root. So in this example, as you know, Is over Us equal to 2 over S minus 3 cube. So it is just obvious that 3 roots are there of the third order system and located at S equal to 3. So this is repeated root at position 3, right? So how we would be able to analyze or define the states in case of the repeated roots? As the order of the system is 3, so number of states would be 3, but roots are repeated. In that case, each and every state would be in terms or function of the other state. Like if we consider the output of the system yt, then it is the function of x1, x2, x3 and ut, that is the unit step. So this is missing ut, right? Now how we would be defining the things, that x1 is the function of x2 state, x2 is function of x3 state, and ultimately x1 is function of x2 and x3 states. So by taking the fractions like this, 1 over s minus 3, 1 over s minus 3 and 2 over s minus 3, here we are considering that x1 is the function of x2s over s minus 3 and x2 is the function of x3s over s minus 3 and x3s is equal the function of us over s minus 3. We have assumed these things. Now arranging these one, so ys equal to, this is your transfer function, ys over us equal to 2 over s minus 3 cube. So this is equal to 2 over s minus 3 squared, and 1 s minus 3, that is the pole, is taken along with this one and considered as state number 3, x3. Similarly, if this is considered as x3s, then ys equal to 2 over s minus 2 squared into x3s. Now, if we take out one of the pole, that is x3 over s minus 3, then it would be assumed as x2s. One pole is remaining, this one. So now, next step, we can consider ys equal to 2 over s minus 3. This is the fraction which was remaining here, and x2s, this is the state we have considered. Then x2s over s minus 3 may be considered as x1s. So ultimately ys equal to 2x1s. This is clear, I think. Now we have to consider for these fractions like this for x3s, for x2s, for x1s, to have the first order differential equation representation of the states to get the state equation of the state space model. So here x1s equal to x2s over s minus 3. This is considered here x2s over s minus 3. Now we can analyze one by one, and x1s by taking cross multiplication like this, x1s into s minus 3 equal to x2s. So x1 dot by taking Laplace inverse, it would be x1 dot equal to, this is going right to the equality sign, so 3 into x1t plus x2t. So this is one state equation concerned to state number 1. Now similarly for x2s equal to this one, this is the expression x2s over s minus 3, sorry, x2s is x3s over s minus 3, this one. So x2s equal to x3s over s minus 3 by taking cross multiplication, x2s into s minus 3 equal to x3s. By taking Laplace inverse, x2 dot t equal to 3x2t plus x3t. Similarly for this expression which is taken from here, us over s minus 3. So by taking cross multiplication, this factor, and taking on Laplace inverse, you would be getting x3 dot t equal to 3x3t plus ut. Now what about ys equal to, it is 2x1 from this equation, right? So yt by taking Laplace inverse, yt is equal to 2x1t. Next slide we will be considering about the state space model in matrix format, simply by taking x1 dot t equal to 3x1 plus x2t. So your elements x1, x2, x3, x3 is absent here, so 3, 1, 0. x1 dot equal to 3, 1, 0 and ut is absent, 0. Similarly for x2 dot t equal to 3, 0, 1, because x2 is absent and u is also absent. So 0, 3, 1, g and ut is also absent, this one. Now for x3 dot t equal to 3x3 plus ut. So here x1 and x2 both are absent. Only 3 is third state with 3 multiplier is there. So 3 and 1 for ut. And for yt equal to, it is 2x1, so it is 2x1 and others are 0. So this is the matrix representation of the system. Now have the block diagram representation. So yt is equal to 2x1, right, and x1 dot t equal to 3x1 plus x2t. 3x1, x1 dot is left to the integrator, x1 dot equal to 3x1 plus x2. So x2t is coming here, there should be a summer connected to input of x1 dot t, and its output would be x2t plus 3 multiplied by x1t. So you have taken x1t from here and multiplied with 3. Similarly, x2 dot t equal to 3x2t plus x3t. x2t is left to the integrator. It is equal to 3 of x2t. So x2t is sensed from here and multiplied by a gain of 3 and feed it to summer where x3 is also as input. Similarly, for x3 dot t equal to, it is 3 x3t. x3t is sensed from here to get x3 dot t plus ut. So in this way we have completed our block diagram representation as well as matrix representation of the state space model. When the system is with purely repeated roots, one thing that should be clear, that all of the roots, that is 3 are 3 are on the diagonal of system matrix A. Now considering another example where we are considering a system which is having repeated as well as distinct root. So here this is the example of the system. We consider that repeated root at s equal to -1, 2, number 2. Two numbers are there of s equal to -1, and one is distinct root, that is the s plus 3. So how? Again we have to expand it by partial fraction. So here we have to use partial fraction method. This is s square plus 6s plus 8 over s plus 1 squared s plus 3. It is taken as a over s plus 1 plus b over s plus 1 squared plus, sorry for this mistake, plus c over s plus 3. So here this is the expression where we have written like this, because whole of the expression, both of the terms should be equal. So a into s plus 1 plus s plus 3, b into s plus 3, because you are getting s plus 1 is squared, which is cancelled, and in c it is multiplied by s plus 1 is squared because s plus 3 is cancelled. So one by one we can consider that s at s equal to -1, if we assume s equal to -1, this term would be 0 and this term would be 0. Only b term would be term with b constant would be remaining. So here at s equal to -1, this is the value of the expression left to the equality sign, and this is 0, this is 0 plus 2b, because s equal to -1, so -1 plus 3 equal to 2b. So b equal to 3 by 2, that is equal to 1.5. Similarly, if we are considering s equal to -3, s equal to y we have considered, because this term would be 0 and this term would be 0. Only c terms would be, c with its constant would be there. So some value which is equal to this, like this, these two terms would be 0, 4c is there, because s equal, we have assumed what, s equal to -3. So -3, s equal to -3, so 1 -3, that is equal to -2, and when it is squared it would be equal to 4c, so it is 4c. So in this way, this is 9 minus 18, 9 minus 1, so minus c equal to -1 by 4, that is minus 0.25. Now for third term you can consider s equal to 0, this is the value, yeah, A by putting the value of B and C, because we got the value of B and we got the value of C. Only a known parameter is A, so A equal to 1.25. Now put the values of constants A, B, C in this expression. Again, this is right. So in this expression, so y s over us equal to 1.25, that is A. Value of A is 1.25, right? Value of B is 1.5, and value of C is minus 0.25. So here it is correct. Now next step, we have to simply have the values or the expression of state equations. So how state equations could be formed? Similarly, on the previous illustrations, based on the previous illustrations, we can have the expressions of states, and this is the realization of the block diagram. I think it was also the example which was no, it is not considered previously, but or I think it should be covered in lecture number 5. So you can take help of lecture number 5. If it is not so, you can query with me. So this is your state space model, where state equations and output equations are there. So the one thing that is to be noted, that all of the eigenvalues or roots of the system are lying on the diagonal. So minus 1, minus 1, minus 3. In this way we have realized the system in Zordon canonical form. Thank you. These are the references.